talking about power computations in chapter 2. It's, again, as I said, it was basically a review. We stopped, I believe, at RMS calculations. So everybody's okay with calculations of RMS. From the basic equation, of course, of RMS, and then we looked at some other RMS of some waveforms based on knowing, for example. So this is the full wave rectified waveform versus the sine wave. So what is the RMS value of a full wave rectified waveform versus a regular sine wave? So if you have a sine wave like this, B max here, and I have a full wave rectified version of it with the same peak value. So what's the RMS value of this? For the sine wave, what's the RMS value of any sine wave with a peak value of V max? V max over root 2. Okay. What do you think is the RMS value of this? Exactly the same, right? So it's exactly the same. And then we did for the half wave. So this is called the full wave rectified waveform. This is called the half wave rectified waveform. So we did this as well. And we said that this has half the area under the root, right? So we said that it's V max over square root of 2 over square root of 2, right? So it was, V max over square root of 2 is the RMS value of the sine wave. This has half the area that we're talking about for the sine wave or the full wave rectified waveform. But, RMS calculations are under the root, right? So we square the waveform, we find its average value and put everything under the root. So if we have half the area, we will put half here. So we end up with, okay, so the equation for this portion is exactly the same as the equation for the sine wave, right? So we will do the integration, over the full cycle. We will get basically half the area. So we can just do the integration over half the cycle and put half here, right? And then we will end up with V max over 2, right? So we did that, and we also did it for what we call neutral current. So we said that these three currents, phase A, phase B, and phase C, look something like this. This is something we will see where it comes from. And if you know the RMS value of IA current, we know that the neutral current, so these three currents will sum up at this node, creating the current flowing back here, which is called the neutral current. So the sum of these three waveforms will be this waveform, which has 3 times the area of IA RMS, which is what we know, right? So we just put the 3 under the root and multiplied it by the RMS value of IA, assuming we know the RMS value of IA, right? So it's square root of 3 times the RMS value of IA. That's the neutral current RMS. Right? So we're just going through some examples here. Again, you don't need to do this, right? You can do the calculation based on the equation, right? You can, put the waveform, write the equation for the waveform, square it, find the average value, take it under the root. You can do that from the beginning. Or if you want to make things easier on yourself, you do some of these tricks. So what does all of this say? Or in equations, what we were talking about, we can represent as equations. So if you have two waveforms that are, the two components of a single waveform V of t. So this waveform can be composed of, a 50 hertz component and a 60 hertz component, for example. Yeah. So what is the RMS value of V of t? So they go through the derivation and then they come up with a nice, sort of final answer that you can utilize all the time. So they go through the derivation, they put, okay, you have a waveform, V of t, that is composed of these two waveforms added together. So they go through and they square it, find the average value, run over the period, integration over the period, they expand this. So after they do that, so they end up with VRMS squared is equal to V1 RMS squared plus V2 RMS squared. Or the RMS value of the final waveform that's composed of multiple frequency components, for example, is equal to the individual waveforms that create that waveform, all under the square root, squared under the square root. So this makes it easy for you to find RMS values of complex waveforms that you have that you can simplify. And I gave an example of that, and of course you can do that for any number of components in the waveform, right? And where would we typically come up with, components that make up a waveform, like the RMS values of frequency components that make up a final waveform? What mathematical tool would we use? Or did you use, or did you learn before? That will, if you have a waveform that's periodic, you can take it up and chop it up into its frequency components. Fourier transform or Fourier series, right? So that's from the Fourier transform or Fourier series, you will be able to get the equations for, or the RMS values for, or the peak values for individual components that make up this periodic waveform that you have, right? So if you have the Fourier series expansion of a waveform, you should be able to find the RMS value of that final waveform using this identity that we came up with. Okay. And it's also very practical as well, and very useful when we talk about DC power supplies. We said DC power supplies will always have ripple, right? We said we will be turning on a switch for a while, right? We will turn on the switch for a while in a DC power supply, and then we will turn it off. Turn it on for a while, and then turn it off. Turn it on for a while, and then turn it off. If this is my output voltage waveform, we said we were going to put a filter after that to filter this waveform. If we filter this waveform, we will get something that will depend on the filter design. So if the filter is such that it filters, again, this blue waveform has a DC component plus a significant amount of AC components, right? Because of all these transitions, it's like the impulse functions, right? It's like the impulse function. So it has a lot of frequency components. For the square wave, I have the Fourier series sheet, and it will, you can write the components of the square wave from fundamental or from DC all the way to a very large number, right? So you've created a filter. You've put a filter at the output before your load. This filter, we said, will do what? It will allow the low frequency components to pass through and filter the high frequency, right? It's a low pass filter, right? So how much of the high frequency components are you going to filter? Right? Typically, when you were designing filters, you drew the gain frequency, or the gain frequency plot of the filter, right? So you were drawing these filters, and you tried to make this gain, for example, equal 1 in the area of signal interest, right? So if you have a signal, and this is a DC power supply, it's producing DC, right? So I would like the low frequency components to pass through with a gain of 1, right? And I would like to filter or attenuate the high frequency components, right? So you will design a filter that does this. So this is where, I don't know, where did you put this cutoff frequency? I don't know, maybe 100 hertz, for example. If you bring this cutoff frequency closer and closer to DC, then remember, you will also have this roll-off here. So there will be a significant roll-off here as well. Otherwise, you will have to end up doing what? You will end up, what did I do? If this is filter design 1, and then this is filter design 2, what is the difference, do you think, from a circuit perspective? How do you go from the same cutoff frequency, same gain in the area of interest, right? So how do you go from this red design to this blue design? What's one approach? What determines your roll-off of the filter? If you have a simple LC filter, or a simple RC filter, or a simple RL circuit filter, versus you have a third or fourth order filter, what happens? You can get a much quicker roll-off. I mean, you can get a much quicker roll-off in this case. So this is definitely a higher order filter. So this can be a simple RC circuit, for example, the red one, and then this blue filter, because of the higher the quicker roll-off, you definitely need to control things better than just a simple time constant of an RC circuit. So this is definitely a circuit, for example, that maybe a LC, so this is a second order filter, or maybe you can add another L here, another C here, and you create a fourth order filter. So have you created, I mean, I'm sure you've done some filter design, right? In 325 or 214, first order filters, second order filters. You have not addressed that? Okay. So anyway, we will talk about it later then. But regardless, I mean, it's typically you will design your filter such that you have a certain gain in a certain area of interest and a certain cutoff frequency, right? And then there will be a roll-off depending on the order of your filter or the complexity of your filter. If you make the filter a high order filter, pretty complex, lots of components, then you can get, you know, closer and closer to the ideal filter frequency response. If you have a simple RC circuit, for example, or a simple RL circuit, you're limited by tau, by the time constant of the circuit. If you apply a voltage across an RL circuit, there's a time constant that you're limited by, right? You cannot change that. It's L over R, right? There's a certain time constant. RC circuit, same thing, simple time constant. But if you have a circuit that is a combination of these many L's and C's, then you have to find the equivalent time constant for a circuit like this. And we can make the time constant for a circuit like this a lot quicker, a lot faster, responding a lot faster than these first order filters. And for now, let's think of it that way, and then we will design, when we talk about filter design later, we will get into more details on that. So anyway, so these DC power supplies will always have ripple, right? That was the objective of the discussion, right? We had this pulse waveform, we put a filter. This filter removed a good amount of the high frequency component, but it left the ripple, it left some ripple. If I choose a filter with, for example, lower cutoff frequency, so what does that mean? I can remove more of the AC component, then what happens to my ripple? So this was my waveform. And for a certain filter, I removed some of the, so this has, again, this has DC plus AC components, lots of AC components. So I put a filter in there so that I can remove some of the AC component. Some of the AC component, if I remove some of the AC component, then I will have the DC component left in there. It will be pronounced, a lot more pronounced, and some of the AC component. The AC component accounts for this ripple. That is ripple. If I give you, if this is the DC component that's in the system, which is the average value of this waveform here, that's the DC value that's in this waveform. That's the 1 over the period integration of this V of t over the period. Right? That's this value here, for example. Right? So that's the average value. And then there's a lot of AC component. This AC component, the amount of AC component that you see at the output will depend on the filter design. Right? So here I've removed some of the AC component. Here I've removed a little bit more of the AC component. Sorry. Right? So less ripple. This one here has a lot less ripple than this initial red waveform. Ripple is what? Is it DC? It's not DC, it's AC. So it's the AC component that's in the signal. So if I filter it, add a filter with a lower cutoff frequency, or add a filter with a quicker roll-off, then I can remove more of the AC component, means I can decrease the size of the ripple. But it costs you more, right? So do you care? I mean, do you need to do that or not? Depends on the specification of your power supply. What I'm trying to say is the output waveform is basically this DC component plus an AC component superimposed on top of it. Right? So basically I had an AC component that looked like this, right? And I had a DC component that looked like this. You add them together, and what do you get? You get this waveform here. Correct? So if you want to find the RMS value of this waveform, what would you do? 1 over the period integration of the waveform squared over the period, all under the root, right? And you would have to find the equation of this line, equation of this line, do the shift of axis, all of that kind of stuff, right? So, or, for example, if I gave you the Fourier series for this triangular waveform, and I did, in the sheet, that the Fourier series sheet that I gave you. I gave you, for example, the Fourier series expansion of this waveform. From the Fourier series expansion of the waveform, for example, you can find the RMS value, like we did for waveforms that have multiple components. So you can find the RMS value of the signal. If you have the RMS value of this signal, the RMS value for a DC value is DC. It's the same value, right? So then you put them both under the square root, square them, and add them, and that will be the RMS value of this new waveform that you have here. So it's written that here. So assuming this the RMS value of this signal is I maximum over square root of 3, right? How do you get that? You can either look at the Fourier series sheet and calculate RMS value, or you can write the equation for this waveform. So they wrote it from 0 to T1. This has a certain slope and y-intercept, and from T1 to capital T, this has certain initial condition, as well as slope and y-intercept as well. So you write the equation for this, and you can do the integration to find the RMS value, right? Which would be horrendous, right? I mean, you have to square this waveform and then put it under the square root. I mean, it's a big mathematical undertaking. Yeah. But if you know that the RMS value of this is I max over square root of 3, and I ask you to find the RMS value of this waveform. This waveform that's a combination of this original waveform, this triangular waveform, plus the DC value. Again, it's this triangular waveform with an offset, right? So you don't need to go through and do this all over again, because again, now you have a different equation because of the DC offset. You will not need to do that again. So you just need to do this. You have your RMS value for this waveform was I maximum over square root of 3. RMS value for a DC waveform is exactly the same as a DC waveform. Square those, put them under the root. That is the RMS value of this combined waveform. Is it okay? It's just RMS. I mean, just calculating tricks to do the calculations of RMS value. Sure. Okay, apparent power and power factor. So in an AC system, have you seen this before? The power triangle. S, P, Q. You've seen it where? 338? Okay. So for those who have not seen it, so in any AC system has voltage and current, voltage at its terminals, current flowing through it, right? And depending on the type of load, then there may be a phase shift between the voltage and the current. What is that phase shift between the voltage and the current called? Exactly. So this theta here, or if the voltage angle is theta and the current angle is phi, then it's theta minus phi, for example. But we'll just call this theta for now. So because of this power factor angle, what happens? So let's say that the power factor angle is 0, right? If the power factor angle is 0, what does that mean? It means that my voltage waveform looks like this, and my current waveform, for example, looks like this, right? That's what this means. And if you multiply them together, what do you get? If you multiply these two waveforms, you get something that looks like this, right? This is P of t. This is the V and I just multiply by each other, right? The two positives will yield a positive, two negatives will yield also a positive, right? And they are the same magnitude, so it will look like this, right? So this is the instantaneous value of power, right? Does it have an average value? It has an average value, somewhere, maybe here. Somewhere here. I mean, you can calculate the average value. Basically, it's 1 over the period integration of this waveform over the period, right? It's the area under this curve, right? So that you divide it by the period. So it has an average value, right? And it's always positive, right? That means power is always flowing from the source to the load. That's what's happening. And power is, I'm talking about instantaneous power, is always flowing from the source to the load. How about if I do this? if I put some phase shift between the voltage and current. So instead of them being right on top of each other, this is my voltage. Excuse my drawing if it's gonna turn out not very nice. But so this is, let's say, V, and this is I. Again, if I want to go through the same exercise, what would I do? Multiply them together. So this will continue, right? So I would multiply together. So I have to look at certain points here of interest. So this is a positive value and this is a negative value, right? So here I will have what? A negative component. Positive, positive, all the way until here. So positive and positive, and I will have something positive here. And then how about here? Here I have a positive and a negative value, so I have something negative here. Here I have a negative, negative and negative, all the way until here is also positive, right? So what you'll end up with, do you all agree? Right, so what we'll end up with is something that looks like, again, this is approximately drawn. You can do it on MATLAB or something simulated. But it will be something like this. So instantaneous power in this case would look something like this. There's a portion that's positive, and then there's a portion that's negative. Right? This is instantaneous power going from, or consumed by the load. Right? If instantaneous power consumed by the load is positive, then it's absorbing that power. If that power is negative, then it's sort of giving back the power to the load. It's generating that power, giving it back to the load. Right? So that's what happens when you have a phase shift between this voltage and current, or what we call a power factor angle between the voltage and current. Right? And this exchange of power between the source and the load is not going to contribute. Does it contribute to the average value? So the average value for this waveform is going to be probably less, assuming this is same Vmax, same Imax, right? Then the value of the average value here will probably be less than the average value here. So this is P1, average value of power in the first case, average value of power in the second case. So I've basically taken this average value of power and reduced the average value of power a little bit. Okay? Because not all the voltage and current, in this case, all the voltage and current was contributing to the creation of average value, a high average value of power. Now some of this voltage and current is creating this value of power that is going back and forth. So this is power coming from my source, and this is power going back to my source. Power coming from my source, this is power back to my source, right? And this exchange of power is what is called reactive power. So there's average power, there's real power, which has this average value here. That's the real power. Real power is what creates torque on a motor shaft. Real power is what we use to light up the lights, right? But why does this other component exist? It exists because we have components in the power system that look like inductors or capacitors. In this case, because the current lags the voltage, right? It's an inductive circuit. How do you know that? How do you know that in an inductive circuit, the current lags the voltage? We know that the equation for inductor is VL equals LdI by dt, right? So what does the current through an inductor look like? I, L is equal to 1 over L integration of V dt, right? So you're integrating the voltage. So if your voltage is very high initially, what does the current look like? It's gonna, fine, you're gonna take bits and pieces of that and integrate and add. So the current will lag the voltage all the time. Even if you have a voltage that's very high right now, and current was 0, what is in the next time switching period? What is the current? You've basically taken a portion of that voltage waveform. Let's say the voltage waveform looked like this, right? You're taking a piece of that and finding the area. Is this the full area of the voltage under the voltage waveform? No, it's a small area. So current is an integration, so it's fine. At this time step, this is the value of current. How about at the next time step? You took another portion of the voltage, find the area under the curve, so it's a little bit more, right? So is current in an inductive circuit ever going to lead the voltage? It cannot, because it's the integration of the voltage. So it's going to come after it. It will always come after it. If I have a voltage, for current to exist, I'm basically taking these small portions of the voltage and adding them up. So you know that if you have a voltage waveform that's leading a current, or a current waveform that is lagging the voltage, then you have a system that is more inductive than capacitive. And if, of course, if there is no inductor or capacitor, then the voltage and current are in phase, which is this case, right? So in this case, I have no reactive power. I have no reactive power. I have a good amount of average power. I also have what? Is this waveform is this waveform DC? It's not a DC waveform. It's actually, it has a pulsating component as well. Right? So this pulsating component is a component that is not contributing. I mean, it's not, I mean, it would have been great if if this is my average value of power, right? It would have been wonderful if this is my average value of power. And if I have a DC voltage and a DC current equal to this peak value, then what? Then I will get average power that looks like this, correct? If these two values are just DC, V and I are DC, what's happening here at these 2 points? I'm getting the maximum value of instantaneous power because these two are maximum. So if I just have voltage and current that are DC, I would have had this value of average power, correct? So for the same voltage and current ratings of a cable, right, if I put DC through that cable versus I put single phase AC through the cable, which will be able to transfer more average power to a load? DC, right? Do we agree? When I put AC now, what happened? I've lost some areas. These areas are basically an indication of amount of power being transferred. I have these areas here that don't have voltage multiplied by current. So these are areas where I'm not able to transfer instantaneous power, which means that my average power has been reduced, right? And that's why people now are talking about high voltage DC. Like people are talking about DC systems, DC power systems, and high voltage DC power systems, like to link to transfer power from a certain area to another, especially for long distances. The most efficient or economical way to do it is using high voltage DC. So why do we then have AC all over? Because there was no power electronics initially, right? So for DC systems, okay, if I have a very short distance and I'm sending power through DC, if the distance is short, or I'm inside this house, or I'm inside this room, can I, for example, can you imagine, for example, this outlet having a voltage of 10,000 volts? From a safety perspective, it's not acceptable, right? It's not an acceptable thing to do, right? So, but if I am transferring a huge amount of power, if I decrease the voltage, P equals V times I, right? So if I decrease the voltage for safety perspective, from a safety perspective, what's going to happen to the current? For the same amount of power, it will increase considerably, right? And then, how about losses? What are losses in a cable equal to? Resistive losses. It's a resistor. Cable is, for example, a resistor, so right? I squared R, right? Or Ri squared. So if I want to transfer huge amounts of power using a DC system, I cannot live with a low voltage that is safe for people to use, right? I would have to step up the voltage to very high values. For you to step up the voltage to very high DC values and then utilize it at the consumer's endpoint, I have to take this huge value of DC and step it down. Can I use a transformer? I cannot. Transformers, you cannot put them. If you put a transformer against a DC a DC signal across a transformer, it will look like a short circuit. Why? Because transformer has, the flux equals the back EMF that you build across the windings of a transformer, right? You remember you have back EMF formed here and back EMF formed here after you supply a winding, right? What did Lenz's law say? Remember this, n d phi by dt? So if I have a transformer winding, oops, if you have a power source here, a power supply, and you have a transformer, and you make this DC, right? If you make this DC, then this E equals n d phi by dt will not be present. It will not be present because there's no time varying flux. Time varying flux is due to time varying voltage, right? So if you put a time varying voltage across a winding, what's going to happen? This winding is going to respond, right? Lenz's law, you do something, something goes by. I don't know the exact terminology, but what Lenz's law says, if you apply an AC voltage across a winding, then this winding, each of these turns, right, will generate a voltage equal to the time variation of this flux with time. So and this time varying flux is due to voltage being placed on the winding. So you put an AC voltage waveform. This AC voltage waveform will push an AC current in the winding. This AC current in the winding will create, again, you have a winding, you have this thing is wound on a core. This core will have what? If you put a voltage here across a winding, and this winding is wound on top of a, this is a magnetic material, what's going to happen? Current will flow through, and when current flows through a piece of wire, what happens? It generates flux around it, right? The flux will flow in a place where it's easier for it to flow, not more difficult, right? So flux does not like air. Flux likes nice magnetic paths. So if you provide a nice magnetic path for the flux to flow, it will flow in it. If you put air, flux will find it. It's like a big resistance to the flow of flux. Yeah. So that's why if you apply a voltage to a winding and you wrap this winding around the core, flux will flow through this core and link all these turns. Right? All these turns in the winding are now linked by a flux. Right? If you go back to DC motor theory, if you have a turn with a time varying flux inside the area of time varying flux, you just have one turn, and you have you put this one piece of wire from your 320, I think, course. You have one piece of wire and a time varying magnetic field. What's going to happen across the terminals of that piece of wire? You will get a voltage across it. Right? That voltage is equal to the time variation of that magnetic field. Right? And if you have many of those turns and you put them in series like we did for the transformer, then you have a voltage. That's a higher voltage that is due to all these turns linked by this flux that's flowing in the core. Okay? So this voltage, where does it appear? This voltage appears here, or appears here on the transformer's winding, right? That's why if this voltage appears and you have a voltage here at the input, then the current that's flowing is equal to what? Superposition. This voltage minus this voltage divided by the impedance of the circuit, right? So it will be some value of current. How about if there is no voltage generated? If there's no voltage, then it's this voltage source. What's the value of current? It's this voltage source divided by the impedance of this wire, which is very low, right? So you've put a voltage source across a piece of wire, right? In this case, because it's DC, there's no time varying flux, and there's no E generated, there's no back EMF generated, right? But if you've put an AC voltage waveform, this AC voltage waveform pushed AC current through the windings, this created flux in one direction. DC current will create flux. But the current created by DC flux, like a magnet, right? When you have a magnet, is there flux around the magnet? Yes. So if you put these experiments where you put the iron powder and you see the lines, etc., right? Are these lines moving around? They're not moving around because it's DC flux. It's DC flux created by the magnet. But if you move the magnet, then the iron filings will move around, right? If you move it around, right? But if you don't move it around, it's a DC flux. This DC flux is not time varying. Because it's not time varying, it cannot account for, it cannot generate a voltage at the terminals of a piece of wire that is in this time varying magnetic field. So now I don't have that. What I did is apply this time varying voltage. It pushed time varying current. This time varying current created a flux that is time varying. This time varying flux, now I sort of guided it to be in a certain area, which by using this core, right? So I have lots of flux flowing through this core. Now all of this flux is linking all these turns, right? So it's linking all these turns. So what Lenz's law says is because you created the flux that made you, I mean, the input current created flux that moved in the core. The flux responded by creating voltage across each of these turns. And the sum of these turns, the sum of the voltage across these turns, is what creates this back EMF voltage. This back EMF voltage is the reason why the transformer input current is not infinite. Right? Otherwise, if you apply a DC across here, then I don't get a time varying flux. If I don't get a time varying flux, then I cannot get a voltage across, a turn of wire that I put in this DC flux. If I don't get that voltage, then I have nothing opposing the input voltage. I have a short circuit. I'm basically creating a short circuit. Right? So, why was I saying all of that? Okay, so why was I saying all of that? After I've created this back EMF voltage, what is the objective of the transformer? It's actually to feed my load. It's not to create the back EMF voltage. Right? The objective is not to create the back EMF voltage. The objective is to pass current through to my load. Correct? So let me redraw our transformer nicely. Right, so this is a nicer transformer. So if I don't have a load, here, then the current that will flow will depend on the impedance. We said here, right? If this is a voltage at the input, this is a back EMF that was created, right? We agree that in the transformer drawing that I had, I didn't even have a second winding. The one where I drew the core, you don't have to have a second winding for that back EMF voltage to develop. You don't need to. But if you put a second winding, what's going to happen? That flux in the core will also link that second winding, creating a voltage, right? So this is how the transformer works. So if you create that voltage, now you have E here, and let's say 1-to-1 turns ratio, so you have an E here as well, right? So if you have some impedance, this is an open circuit, if this is an open circuit here, and you have some impedance in this circuit, then some current is going to flow to create this flux, which creates these E's. This current is a small amount. Dr. Haytham probably called it excitation current in a transformer, right? Or the magnetizing current. Remember that you were drawing the magnetizing current? So this is the excitation current of a transformer. This excitation current, is it used to transfer power from my source to my load? It's not. It's not transferring power from my source to my load because I said the load, there's no load here, it's open circuit. But is this excitation current necessary or not? Yes. It's necessary because it's doing this E thing, right? It's creating this back EMF voltage. It's creating this back EMF voltage through this creation of flux, right? So it's basically looks like an inductor to my source, right? So it's gonna cause current to sort of have some, if you were drawing this current to be 190 degrees from your resistive load current, for example, if you remember something, or you're drawing the magnetizing branch and the core loss branch, and each one of them was 90 degrees apart, all that kind of stuff. You remember that back then? But anyway, so the current that's coming in here, if there's no load, this current will be a small amount, and it's basically used to set up the magnetic field to create this back EMF voltage, right? And this is what in the system we call reactive power. Because is current being consumed to do this or not? To create this back EMF voltage? Is current being consumed or not? Current has to flow. Current has to flow. A little bit of current will have to flow to create some flux, to link the turns, to create a back EMF voltage. There is current flowing, and that's the magnetizing current. It's a small amount of current, but it's there, right? Even if I have a resistive load, my load is resistive, purely resistive. But is the source supplying only the resistive load? No, it's supplying the transformer and the resistive load, right? So this magnetizing branch is consuming the reactive power that's in the system. The reactive power that's in the system is something that this magnetic field, after you set up the magnetic field and you collapse it again, right? When you collapse the magnetic field, assuming there's no resistor in the path, there's no resistance in the path, what happens is that power goes back to the supply. That's exactly what happens. The power that was used to set up the magnetic field goes back to the supply, assuming that there's no resistive loss. And that's what's called the reactive power. So reactive power is power that is exchanged between the source and the loads to set up things like magnetic fields for transformers, to set up things like magnetic fields in motors, right? The magnetic field in the motor is used to do what? To link the stator and the motor, so you have two magnetic fields that hold on to each other and they move together. For example, it's simplistically, right? This magnetic field is set up using reactive power, exactly the same phenomena. It's set up using reactive power. Is it used? Is it beneficial for is it going to affect the amount of average power that you see at the shaft of the motor? Is it like, okay, here is the amount of power consumed to set up this E, this back EMF voltage? Is it affected by the amount of load that you have?
Yes.
Is it?
Well, if your stator goes out in your boat, you can't go over a certain amount.
You've set up. No, let's talk about the transformer for a little bit, right? So now we've set up this magnetic field. Does it matter if I have a load or not? You will see a voltage at the terminals of the transformer. You will see. At the secondary, you will see. And at the primary, you will see this back EMF voltage, and the current will not be very high. Why? Because you've set up this magnetic field. This magnetic field will have a value E. This value E will not change if you put a load. It will still be there. When you have a transformer that has terminals at output terminals 100 kilovolts, right? 100 kilovolt transformer. If you remove the load, is the voltage going to change? You have a transformer. It's 100 kilovolt output. The output voltage will be 100 kilovolts, whether or not you have a load. If you put a load in there, more current will flow. So you may have some voltage drop, small voltage drop due to the resistance of the circuit, right? But the amount of current that's being drawn here to create the magnetic field does not change. So there's a small amount of current to create the magnetic field. That's the magnetizing branch current. And then there is a lot of current flowing through the system, coming from the supply, through the transformer, through the magnetic field, to the load, to feed the load when it's there, right? And the motor is the same. If you set up the magnetic field, let's go back to what was your question about the motor?
Well, it was in our boat, the stator went bad, and you could go slow, but as soon as you tried to give it more to go faster,
Yeah.
The stator wouldn't fire properly.
Again, maybe it's electronics, right? Maybe they. So maybe what?
Wires and made the wires not.
So something, yeah. So what happens maybe is some of these turns get shorted, right? And for you to control the speed of a motor, what do you do? In 338, Dr. Haytham was talking about induction motor speed control. What were you doing to increase the speed of an induction motor, for example? You're applying more voltage, higher frequency, right? The V over F ratio, remember that? So you're applying more voltage. So if you're applying more voltage and you have lots of turns that are shorted, what's going to happen there's a lot of current will flow in these turns that are shorted and causing a lot of current to flow from the input as well, because the input source now is seeing a larger short circuit, is seeing less impedance. So maybe the input power supply could not cope because of the stator turns, some of them being shorted, right? So are we going to have, if some of these turns of the transformer are shorted, am I going to have some voltage or not? I will have, but this will also cause the current coming in to be higher. So the magnetizing current will go high, will become higher. At some point, maybe my power supply at the input cannot cope. That's a different story, right? And of course, eventually, if there's a If there are some of these turns are shorted, that means there's a local heating area, and it's not made for that. Again, these wires are insulated, and now you've broken the insulation, and now you're just adding lots of losses in this small area, and these losses are heating up the place and bringing down the insulation, and eventually go bad. Goes right. So that can happen eventually, but the idea is this magnetizing current is set up by this magnetic field. Right, so this magnetic field that's linking the two turns is set up using the reactive power coming in. It's current that is not in phase with the resistive current. Right, you were drawing magnetizing current into the transformer at the 90 degrees with respect to the resistive, the core loss component. Correct. So it's exactly like a voltage source across an inductance. If you voltage source across an inductance, what will the current? If you have voltage source across an inductance, the current will lag the voltage, right? By how many degrees? If the voltage is sinusoidal, this will be cosinusoidal or vice versa, right? Differentiation of a sine is a cosine. Integration of a cosine or differentiation of a cosine is a sine. Forget about the negative signs, right? So if one is a sine, the other will be a cosine or a negative cosine, and vice versa. So there's a 90-degree phase shift between them. Right? So there's a 90-degree phase shift due to this magnetizing branch. But then you have a big resistor here. So the sum is some inductance, some inductive current, and a huge amount of resistive current. So now the total current, is it going to be in phase with the voltage? No, because it sees some inductance, so it will lag the voltage by some power factor angle. How much is this angle? It depends on the value of R and depends on the value of L and if you have C's or not. Right? So, and the fact that you have this power factor angle is a clear indication that there is reactive power flowing in the system. So now, is this reactive power useful for creating the light that we see? The light that we see is produced by average power. The torque on the motor shaft is produced by average power. It is not produced by the reactive power. But the reactive power is needed to set up the magnetic field. It's a magnetic field. Magnetic fields are inductors, basically. These inductors are going to consume current that is 90 degrees away from a resistive load. Right? So it's going to inevitably require some reactive power to set up the magnetic field of a motor, to set up the magnetic field of a transformer. So all of these components that have some magnetic fields in them require reactive power. And this reactive power is something that does not produce the average torque, does not produce the light intensity, it is not contributing to average power transfer. It is reactive power that is helping basically set up these magnetic fields. But this reactive power, does it have current and voltage associated with it or not? If I don't have a load, we said that there will still be current flowing to create this E. Right? So this is the current associated with the reactive power. This current, it's flowing through cables. Right? These cables have resistors or have impedances. They will cause voltage drops, they will cause power loss, and they're not contributing to average power transfer. Right? So typically, the more of this reactive power you have in a system, is it good or bad? If you have a lot of reactive power in a system, is it a good thing or a bad thing? We said it does not contribute to average power transfer, does not contribute to motor torque on the shaft, does not contribute to light production, does not contribute to anything we want. It's something that we have to live with. So we have to have transformers in the system because we want to step up AC voltages, step them down. To have a transformer, we have to live with the magnetic field being required to set up. So we have to live with the fact that we have to have some reactive power being consumed by the transformer. The system will consume reactive power. But this consumption is not something we would like. It's something that we have to live with. Okay? Because it's extra current flowing through the system that is not contributing to power delivery. It does not contribute to real power delivery. It does not. You cannot charge a battery with reactive power. You cannot. Right? It's power that's used to set up magnetic fields and collapse them. Remember, magnetic fields here are time varying. And transformer, it has to be a time varying magnetic field. So you set it up, You collapse it, bring it in the other direction. Set it up, collapse it, bring it. You follow the hysteresis curve, right? And that's where the exchange of power between the utility and the source, the load and the source is, right? So that's this negative portion that's coming back and forth. So this negative portion has an associated positive portion that goes back and forth between the loads and the supply. And that's a reactive power going back and forth. Okay? So reactive power exists, and it adds more current. So I cannot rate my equipment if I have a system that needs to feed a 100 kilowatt load. That's a purely resistive load that's rated in kilowatts only because there's no inductive component to it. It's only real power that's consumed in a resistor. Then if I have to feed that load through a power system that has transformers and machines, etc., etc., I cannot ignore the fact that there is current, extra current in the system due to the fact that I'm generating that using a machine. I'm generating power using a machine. I'm transferring the power on these cables. These cables are basically conductors with current flowing through them, meaning they have some equivalent inductance. I have transformers. There is an additional equivalent inductance to the transformer. So I have to feed that reactive power, to feed that load, which is consuming only real power. I'm going to consume some reactive power along the way. Right? I'm going to consume this reactive power along the way. So I cannot rate my equipment. For example, now this transformer is feeding this load that's 100 kilowatt. I cannot rate the transformer to 100 kilowatt, which is the rating of the resistor. I cannot do that. Because this transformer is also seeing what? It's seeing that 100 kilowatts pass through, because that's what happens here, right? The load current will eventually pass through from the supply as well. But it's also seeing the reactive power used to set up the magnetic fields. So I have to rate it to something that is a combination of the active power that's consumed, which is the real power that's consumed or consumed by the load, as well as the power that's consumed to create these magnetic fields. Right? So that's the real power that's consumed is called average power. That's the real power. This is the 100 kilowatt we were talking about, 100 kilowatt that we were talking about, right? And then there is some power associated with setting up these magnetic fields, and that's the reactive power. So I have to rate my equipment to something that takes into consideration the fact that we have a certain amount of reactive power in the system. And that's what's called apparent power. Apparent power or complex power. So S is apparent power or complex power. S as a magnitude is equal to all the voltage that's coming from my supply, multiply all the current that's coming from my supply. Right? It's V times I. Everything, all of it. That's because I have to account for that. That's how I rate my transformer. Because my transformer can be feeding a resistive load. Fine. It can be feeding an inductive, highly inductive load. What does that mean? I have a huge amount of reactive power that's going to go through the transformer to feed the inductive load that requires this magnetic field to be set up. Right? So I cannot rate my transformer to real power. I have to make sure that I account for the fact that I have some reactive power in the system. Right? So all AC equipment is rated to what is called apparent power, or volt amperes. VA. So it's VRMS times IRMS of the system as a magnitude. Right? It's VRMS times I. It accounts for all the voltage, all the current. Right? Now, part of that is going to feed my resistive load, which is a consuming real power. That's where the real power consumption is, and that is equal to what? If this is my power factor angle, because my power factor angle, or the angle between the voltage and current, is what dictates how much reactive power I'm consuming. Right? If the power factor angle is 0, what does that mean? That means my source is feeding a resistive load. If there is a power factor angle, that means my source is feeding an equivalent inductive load, has a resistor and inductor in there. Right? So the power factor angle is an indication of how much reactive power you have in the system. Right? So now if you want to calculate your active power and reactive power from your apparent power or complex power, P equals what? S cosine theta, right? And Q is equal to S sine theta, right? Okay? Where theta is the angle between voltage and current. Okay? So this is very important. And one other consideration is power triangle. That I know you took it, but just out of review. this will sound a bit distorted, but if voltage is, if I assume this is the angle of my voltage, it's my reference voltage, and current is here, and the angle between them is theta, so current is lagging voltage. If current lags voltage, you draw Q as a positive value. If current leads voltage, where would you draw Q? At the bottom down here, right? So the apparent power would be here, S would be here. Okay, so it's a bit, it's not very intuitive, right? Because here current is lagging, so it's at the bottom, but the reactive power is on the top. And the opposite happens here. If current is leading, reactive power is negative, and it's drawn to the bottom here. So this is an indication that I have a capacitive circuit. This is an indication that I have an inductive circuit. Okay? Any questions? Okay, so that being said, so we went through the power triangle. So again, we said that the apparent power or complex power is a quantity that accounts for everything flowing in the system, and that is what you rate your equipment to. So you will find the transformer, if you open up a transformer data sheet, it will be rated to X, Y, and Z megavolt ampere or kilovolt ampere, or it will not, or volt ampere. It will not be rated to so and so kilowatts. It will not be, right? Because of what we just talked about, because of the power factor. Okay, and power factor will be P over S. Again, this is just from the trigonometry, right? If you go to the triangle, we will find that, we said that apparent power factor is cosine theta. This is called power factor. And we said that P is equal to S cosine theta. Right? So this is power factor. So power factor is equal to P over S, for example. Right? So this is just the trigonometry, right? Okay, I know it took a lot of time here, but this power triangle is very important, okay? So it's the next part I will go, we went through a lot of this. So something else that's interesting. So we said that even in a system where I don't have a difference between voltage and current, we saw that the waveform for power, instantaneous power, looked something like this, right? There's no negative, and it had an average value. This is instantaneous power in a resistive circuit, right? This was the V times I when they were in phase. This has an average value as well as some AC component, right? Any waveform that is not pure DC, it means it has an average value for a DC component and some AC component. So even if the circuit is purely resistive, we saw that it has an average value, the power, and has an AC component. This AC component does not contribute to real power transfer, does not contribute to the average value of power. But it's there, it exists, right? And you see it in the equation here, right? So if I take V multiplied by I and do the expansion, I will get, V max, I max over 2, or V max over square root of 2, I max over square root of 2. So V RMS times I RMS, right? Multiplied by cosine 2 omega t, blah, 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 and then plus cosine theta minus phi. This is the pulsating component that does not contribute to average power. Because what's the average value of a cosine waveform? 0, right? A cosine waveform or sine waveform has an average value of 0. So this disappears in the average power calculation. This is a fixed value, right? This is the angle between voltage and current is a fixed value. You multiply, so this is VRMS, IRMS times cosine the power factor angle, right? And that's where we get our equation for average power from. Right? And then from the power triangle, we can calculate the reactive power consumed by the system, the average reactive power. Right? And of course, complex power or apparent power we said is a complex number that has to account for both. Right? And we saw that from the power triangle. Its magnitude accounts for all the voltage and all the current flowing through the system. So it's the RMS value of the full voltage, full current. Right? And we talked about the power factor equation. So any questions on this? No? And we see where this goes away? Okay. Something else. Power computation, non-sinusoidal periodic waveform. So if you have power electronics, right? Power electronics is creating waveforms. You take an AC waveform to create a different AC waveform. For example, in a wind application, or you take a DC waveform that's pulses of DC pulse or a square wave pulse, and you create another DC waveform that is nice, smoother. For example, you've removed some of the ripple. So, in this case, for example, you had a resistive load. For example, that's a linear load, or you had a battery. Battery is also a linear load, right? But what if you have a nonlinear load? That's a different case. So in the case that we just discussed, we have a source that is not pure AC or not pure DC, meaning it's a combination of DC waveform plus lots of AC components, feeding a linear load in this case, right? So what would be the power consumption, or the power consumption of the load? We would have to account for what? This voltage waveform feeding this load. This voltage superposition, right? If you have many of these sources and you have a load, resistive load, you would do superposition, correct? Take all of them out, use one, then add them up, and then figure out the final value of current. This final value of current is the sum of the contribution of these individual power supplies, right? Feeding that load, right? So you can find its RMS value by the identity that we talked about at the beginning, right? If you know that this is V1 cosine some angle, then the RMS value is V1 over square root of 2. Divided by, if you want to find the current, if this is a resistor R, then the current corresponding to this source is V1 divided by square root of 2, that's the RMS value, divided by the resistance. Right? So RMS value divided by RMS value divided by resistance. So you can find the current contribution from each of those. If you find the current contribution from each of those, you find the full current. This full current is not sinusoidal. So what we do is, to ease or to make our life easier, if you want to do some calculations of power, we will apply Fourier series. Again, to calculate, if I have a waveform, a source that is not a pure AC or not a pure DC, and I want to know how much power is being consumed by the load, I can try to draw the equation of come up with the equation of the source, right? If I have the equation of the source that's generating something that looks like this, right? I can try to come up with an equation for this, if this is periodic. You can try to do that, right? I'm asking you, what is the power consumed by the load? And this is the voltage feeding a resistor. How can you come up with this, right? You cannot, this is not the sinusoidal waveform where you can say the RMS value is V maximum over square root of 2, so the power consumption is I squared R, right? You cannot, it's very difficult to come up with an equation for this. Maybe you can, right? The alternative is to do what? Take this waveform and chop it up using Fourier series and find these individual components. I'm not asking you to do that. I will give you Fourier series equations for certain waveforms. That's it. It's not a Fourier series course. And then from the Fourier series results, you will know what? From the Fourier series, for example, if this is the waveform that you're applying, the Fourier series for this waveform v of t is v maximum over pi cosine omega t, cosine 3 omega t over 3. So it's the fundamental, third harmonic, fifth harmonic, etc., so on and so forth. Right? So from the Fourier series, you know the equation of each of these sources. Right? So now if you know the equation of each of these sources, and then you want to find the power that's being consumed by the resistor, now you can do that. Because you have the equation for the first fundamental components, v maximum, 4v maximum over pi cosine omega t. And then what's the RMS value of that? What's the RMS value of the fundamental component? No. How is 0? RMS value of the fundamental, this is a Fourier series, right? The Fourier series takes your waveform and chops it up into its components. The fundamental component is the first harmonic. So the first harmonic is, the equation for the first harmonic is 4v maximum over pi cosine omega t. What is its RMS value? 4v maximum over pi over square root of 2, right? So that's the RMS value of the first component. Then you can find the power consumed by the resistor due to the fundamental component. It's IRMS squared times the resistance, right? So you found that for the fundamental. Then you found that for the third harmonic. Then you found that for the fifth harmonic. Then you found that for the seventh harmonic. So you can approximately tell me, okay, again, because this is going all the way to infinity, right? At some point you have to stop. You cannot go to infinity. At some point you'll have to stop. And when do you stop? Again, at some point, again, these numbers become very big. So if you take a number divided by a number that's very big, the magnitude becomes irrelevant. At some point, the amount of power that's being transferred by the source at higher frequency, at some point it's going to become irrelevant. But if you want a 100% exact solution, then yes, you have to go and all the way to infinity, take all these components and calculate the power due to each of them, right? So here, what you would do is, again, I give you a waveform that is this square wave. The square wave has an average value. No, it doesn't. But assuming something, I gave you something with an average value, then you would take account for the DC source, account for each of the harmonics to figure out how much power is being consumed by the load or transferred by the source, right? And then the tool is the Fourier series. And we will not, I don't ask you to go through and do Fourier series. You will not be asked to do that. The maximum is you'll be given the Fourier series sheet that I gave you, but you just need to know how to use it. I mean, this Fourier series expansion for this waveform, whether it's voltage or current, right? It just happens to be voltage, V of t there. But if it's the same waveform for current, then you have whatever you need to calculate, right? So again, we're not going to go through the Fourier series. It's just a mathematical tool that you've learned before, and I will give you the waveforms, the Fourier series for the waveforms that I need. We agree? That's this sheet that I have there. And this is what I was talking about from a power transfer perspective, right? So if you have the Fourier series representation for a certain waveform, so this is the Fourier series representation for the voltage. So all the voltage harmonics, you know the equation for them. That's from the Fourier series sheet. All the current harmonics, you know the equation for them, right? If you would like to calculate power, average power is 1 over the period integration of instantaneous power over the period. Instantaneous power is the multiplication of each of these components by each other. The DC component will create some DC power transfer to the load. The first harmonic will create some first harmonic power transfer to the load, so on and so forth, right? Everybody's okay with this? It's fine? So what if I have, so this is the case where I have a non-sinusoidal source and a linear load. Linear loads will respond to by just, maximum they will respond by a phase shift to the source, right? If it's an RL load, it will provide some phase shift, but at the same time, but the frequency will not change, right? If I put a 50 hertz signal on a RL load, a linear load, right? Then the output current will also be 50 hertz, right? How about if I have waveforms that are different frequencies? If I have voltage at 50 hertz and then current at 60 hertz, is the multiplication of this going to provide some average power? Two different frequencies. Think of it in an easier way. Think of a waveform where you have a DC component and a 50 hertz component. If your current is DC and your voltage is 50 hertz, will average power be produced out of these components? If your current is DC, for example, and your voltage is AC, somehow, if we're able to do this somehow, right? If this is the case somehow, then what is the power delivered by this source? What's the average power delivered by this source? And we have to go back to our basics, right? What is average power? It's the integration of instantaneous power. Instantaneous power in this case is this multiplied by this. So it's the voltage waveform basically scaled, right? It's V times I here, V times I here, right? So what's the average value of this waveform? Yeah, equal magnitude. So it's 0. So anytime you have voltage and current that are not the same frequency, right? Then there will be no power transfer due to that, right? And when does this happen? It happens a lot in power electronics, actually. So that's our next section here. We talked about this. You have a sinusoidal source and a non-linear load. So first we talked about non-sinusoidal source and a linear load, right? The loads will respond to each harmonic by providing a current. If you have a source of voltage at 50 hertz, you put a load, it will give you a 50 hertz current. 100 hertz will give you a 100 hertz current. 150 hertz, 150 hertz current, right? Each of these currents multiplied by each other will contribute to this equation. V0 times I0, V1 times I1, V2 times I2. All of that will contribute to power transfer, average power transfer to the load. But now, if I don't have a linear load, if I have a nonlinear load, what does nonlinear load mean? Nonlinear load means I provide it, let's say, with a sinusoidal voltage, and then it responds by giving me a current that looks like this. Is this what you would expect if you put if I put 50 hertz? If I put 50 hertz to a load, you would expect to see 50 hertz current. That's only in the case of a linear load. If the load is nonlinear, then it's going to respond somehow. This somehow will contribute to nonlinear current. So if this is a V, you will supply it with a nice sinusoidal voltage at 50 hertz. It will respond, it will consume current that looks like this, or current that looks like this, right? This is not the response of a linear load. It's a response of a nonlinear load. So in this case, what do I have? My source is now generating what? A voltage that is 50 hertz, right? Correct? It's generating a voltage at 50 hertz. How about the current that's being drawn out of my source? It looks like this or like this, right? These waveforms, are they nice pure sinusoids? They're not. They're probably occurring at the same, they're occurring at the same, they're periodically occurring at almost the same period as my input voltage waveform, or double it, or half of it, or something like that, right? So if you do the Fourier series for this waveform, or this waveform, what will you get? This waveform is easier. Let's say that this waveform, this is my voltage, and this is the corresponding current. This is V and this is I. This is nice 50 hertz. How about this? This is occurring every 50 hertz, so it will have a 50 hertz component. We agree? It will have a 50 hertz component. Does it have an average value? If these are equal in area, it will not have an average value, so it will not have a DC component. But it will have some other components, some other AC components, third, fifth, seventh, blah, blah, blah. Right? These are all currents that are actually flowing in my system, right or wrong? I mean, this waveform is actually flowing, coming from consumed by my source. The circuit is forcing me to draw this much current. So these components of current are at 150 hertz, 200 hertz, whatever, at other frequencies, and at 50 hertz as well. So what is the average power being drawn or consumed by the load, or drawn from my source? The average power will only come from what? From the 50 hertz voltage component and the 50 hertz current component, right? Two people are walking, okay? Two people are walking together, right? If they're holding the same stick, they're trying to walk together. If they're moving at the same speed, then everything will be fine, right? If one is faster than the other, then they will just do this, right? If one is just faster than the other, they will always do this. Or one is slower than the other, they will do this, right? And they will do this at different speeds depending on how fast one is with respect to the other, right? So this is not contributing to motion to forward. It's not contributing to you pushing this load that you're trying to push. You're standing in your place. Right? So there's no average power being consumed or transferred there. Same thing with the voltage and current. So I have a voltage signal at 50 hertz. Current, because my current is, I'm feeding a nonlinear load, this nonlinear load is not responding with 50 hertz current. It's responding with 50 hertz, 100 hertz, 150 hertz, all of these. And there's no voltage corresponding to the 100 hertz, 150 hertz, 200. There's no voltage. The source is not supplying that voltage. It's only supplying 50 hertz. So what is the power delivered by the source? The real power delivered by the source. It's only the 50 hertz voltage multiplied by the 50 hertz current. Then cosine the power factor, right? That's the real power transfer. But there's lots of other components. These other components are called harmonics, right? These other components are called harmonics, and they cause a distortion in the sinusoidal signal. They distort the sinusoidal signal, but they exist. If current is flowing and exists in a system, what is it going to do to the cable resistances, and then transformer resistances, and the motor resistances? This is actual current flowing. It will cause power losses. So these harmonics will cause power losses in the system. What will these harmonics do to my apparent power rating of my transformer? Remember, we said apparent power or complex power, the rating of a transformer is all the voltage's RMS value multiply all the current's RMS value as a magnitude. So then I'm going to calculate the RMS value of this waveform, not only the fundamental. So there will be a lot of extra harmonics that are flowing in there, so that it contributes to increasing the complex power or apparent power rating of my system components. So these harmonics are really bad, right? They cause you to buy more expensive equipment because you have to rate it to larger values. They cause losses in the system because there are currents that are flowing, right? But we have to deal with them because this is what power electronics does to a system. Power electronic circuits are nonlinear loads. They don't respond like a linear load unless you control it to look like that. That's something else. So we'll stop here for now. We'll continue next time.